We have Dr. Jayati Sengupta with us to deliver a lecture on macromolecular dynamics flexible fitting into cryo-EM maps. Dr. Jayati Sengupta did her PhD in Central University Shillong, and then she moved as a postdoctoral fellow in Wadsworth Center, Albany, with Professor Joachim Frank. She has stayed there for more than 8 years and extensively done work on single particle cryo-EM, and she is currently a senior scientist. What is that designation? Principal scientist in IICB Kolkata, and as you know, she is one of the two people who has the TEM in India for biological FEG TEM, and very few facility in India. She is taking care of one of them, one of the first two facilities in India. So I'll give the mic to Jayati so that she can give the talk.
I will be talking about this flexible fitting into cryo-EM map. So far you have already learned all the techniques exhaustively, I believe, to get a cryo-EM 3D map. Maybe 5 years back I would have safely could tell that a medium resolution cryo-EM map. But today I can't say that because many people will say, no, we get atomic resolution. Yes, due to some technical achievements and softwares, these techniques really revolutionized the cryo-EM field almost overnight. So many projects people get high resolution, near atomic resolution structure, but still we get moderate resolution, say 7 to 15 angstrom maps for different projects. And still, as a structural biologist, we want to see structure as atomic models, not this topological thing like all. Without this atomic structure, we used to call this as beak, as spar, as shoulder, like that. So we want to see this map in some atomic description. We like to see it. So that is the hybrid approach, what Dr. Natesh already mentioned, that molding the crystal structure or NMR structure into the medium resolution map. That's the routine work in the cryo-EM field, used to be at least, and now also it has some application. So when Natesh mentioned that nowadays, since cryo-EM reached the atomic resolution, people think that X-ray people, they are losing their job or something. I remembered in 2000 when this millennium structure came, the ribosome crystal structure solved. That time people said the same thing was going around, that who will do cryo-EM, because even crystallographers can solve such a big structure. So yes, that time it was like cryo-EM people were going to lose their job, and now people are thinking the other way. But no, it's actually complementarity, supplementarity, all those things, as you heard from Natesh. So we are trying to get better structure through synergy, and actually Michael Rossman, he showed in this paper that, sorry, that the accuracy of any structure molded in a cryo-EM map is actually the accuracy depends on the resolution, and it's about the factor of 10. If the resolution is say 17 angstrom, then the structure you mold into it is about 1.7 angstrom, plus minus error would be there. So the better resolution, definitely you fit your structure better. This table, actually Fujiosi long back, he made this table, which is approximately 7 angstrom you need, below 7 angstrom to really see the helices, at least predict where the helices could be. And you really need better than 3 angstrom resolution. So initially when it was 20 angstrom, there was rigid body kind of fitting. And then the better the structure, different methods evolved. We know that why we want to do this flexible fitting. We know that this proteins, they are actually weighted average of many structures. And can we really say in cryo-EM map what the structural differences in these regions? After ligand binding, this changes, and it has a different weighted average again. We cannot say. So what we can say, how much we can really say as a low resolution or medium resolution maps. So most of these proteins, they have many domains, big domains, and each of these domain, many times they function, they have a specified function, and they function, each of these domain, they perform their function by some conformational changes. And these changes actually could most of the time are based on this hinge motion. Like say this is a elongation factor TU, EFTU we call. This has yellow one you see, that is a switch one region where the GTP binds. This changes from GTP to GDP state from about 310 helix, I think, it changes to a beta sheeted structure. Can we see that kind of changes? We cannot. We cannot really see even probably 4 angstrom. It needs to be much better than 3 angstrom to even model this. But we really can see directly, you can make out that these domains, they are how they are arranging on these linker regions. That's the hinge region. Most of the cases we really cannot say anyway the changes, if anything happens inside the domains. But even at medium resolution, we can really see this motion of the each domain, inter-domain kind of motions. And what happens to the macromolecules like ribosome, which has 50 proteins, 3 big RNAs, and then several factors, and then tRNAs. So each one has got some motion, but they really work as a concerted way. I mean, they need to orchestrate very nicely to perform the function. So there are actually bigger motions of the whole ribosome, or it is true for any other, say, GRO-EL, which has a GRO-ES bound form, and then protein bound form, different forms, and it really changes conformation. But how, if a big changes in the structure, which is really visible here in this movie, but if you really can explain it at atomic, with some atomic structure. Can we really say that atomic structure is an accurate one? No, because it has really associated errors. Probably the C alpha or phosphate backbone, they are some like 1 angstrom plus minus error or 2 angstrom, but all the side chains predictions, they are not correct. But what can we really do on that? I mean, just with that atomic model, which is called pseudo-atomic, quasi-atomic model. How much we can tell on that? So initially, as I told, there are all interactive manual fitting methods that when the resolution was really not very good. Then the computerized automated fitting came into picture, and the automated fitting was also as a rigid body that time, only to avoid the error associated with human error. But then with resolution was in more and more getting better, and then the flexible fitting came into the picture. Now, if you have a map less than 5 angstrom, Professor Garib's program software is there, you can use that. But if you get a 7 to 15 angstrom map, there are still some way where you can generate some quasi-atomic models. And I'll describe a few of those methods. Definitely as an user, I'll describe, not as developer. As in the morning, I think Dr. Lugan mentioned that if you really want to use a software, you ask a developer. So, but just allow me to describe other people's method, which I just uses. And if you really want to use any of this, then yeah, it's better to go through for all this tutorial and all this there techniques. So Citus is a very like oldest, one of the oldest, at least I know that's the oldest method, which actually first came as a for rigid body fitting, but then they have introduced some flexible fitting protocol in that. And then the real space refinement package came, and then normal mode based fitting, and then molecular dynamics based fitting. Okay, so Citus was actually, it's a like coarse grain model. It just reduced representation of both the map and the coordinate. It's called vector quantization, they say. It's like code book vectors. It just minimizing this vector and this map vector, the best fit it finds. And then they incorporated this kind of skeletal motion. In the 3D motion picture, they use this kind of method. There's a constraint on this vector so that it just moves and fits here. This really gives a slightly better result because it keeps the secondary structure almost intact. But this was used, say, when the maps were to 20 angstrom, 25, 30 angstrom. Then the real space refinement method came, which actually I think that's the first try to use X-ray optimization method for cryo-EM. It's Michael Chapman used this. Yeah, I forgot to mention that the CITES was actually Willy Rieger's group, they made it. And this was Michael Chapman. He made this module, real space refinement, RSREF. Initially, it was with the TNT, and then afterwards it was with CNS. These are actually crystallographic for model optimization. These programs are used, and then RSREF is incorporated using this TNT or CNS modules, because they have all the stereochemical restraints for X-ray package. Using X-ray package is really good that way. And what the method actually uses is the fitting. You can really use your crystal structure. It's a big crystal structure in different pieces, number of rigid bodies, many number of rigid bodies. And first maybe a smaller cut in the structure, and then you can go higher once it fits some round, and then you can use it more smaller rigid pieces. Like I can just tell that it's the RNA 16S and 23S RNA. Each of these helices you can cut as rigid pieces. Cutting means you have to mention that this is a rigid piece. And then even the proteins, if they have bigger 2-3 subdomains, you can just mention that they are separate rigid bodies. So like rigid pieces, piece by piece it fits. And yeah, it definitely it's not giving you the perfect, the most accurate atomic structure, but it could tell at some quasi-atomic level. It was actually used for two maps. One is elongation factor G bound and unbound ribosome, where this elongation factor really binds and inducing a very big change, which is called a ratchet motion. The 30S subunit actually ratchets on the 50S. That's a very big change, and this change actually can be seen in this when these two structures were modeled using this method. And since it was piece by piece, you can really see the motions of the helices. And I don't know if how to. Yeah, so you can see these motions of the two, which are called the stalks, end stalks. So it's really not the perfect structure, but it shows these two stalks, which are called the L1 and the L7, L12 stalk. It really moves during the different course of translation, different steps. So this much it could be predicted from that modeling. So, and then it really shows the kind of B factor of which regions are more flexible and which are more, the core regions are more stable, and then the 30S is more means unstable than the 50S large subunit. So it's limited information you can get. And then comes the normal mode based method, where this normal mode, the vibrational modes, as you know. Now, for a big molecule, fitting normal modes are very difficult. So they use a very coarse method, like using a harmonic harmonic potential and all this very crude way to model. So definitely it won't give the high frequency normal modes vibrations perfectly. Definitely it cannot, but very interestingly, for a big molecule, when you compute normal modes, the lowest normal modes, what it gives, that really shows some correlation with a large motion of these macromolecules. So that really inspired them to do this, use this method as a fitting method. Like the L1 stock motion, what I showed, when this was done by Florence Thoma and Charles Brooks, who made this CHARM-M force field. When they saw this, in one of the lowest normal mode, they could see that L1 stock motion. So then they tried to make a normal mode based fitting method, and actually here I saw that even the tRNAs, they were actually initially thought to be very rigid molecules. But during this fitting course, we really found that they are very, very flexible, and they can really mold itself different ways to go through the inter-subunit space and all this. So this normal mode is actually this elastic network where each amino acids, you can just think of a ball or the C alpha atoms, and then it is the bonded with another one, and it's just vibrating, that model. And then when you are using it, it's as a fitting approach. What they do, that some vectors they took, that is the direction, only the direction it can give, which are few lowest frequency normal modes. So it can only give you the direction. The amplitude of the motion is really arbitrary. It really, you need to see in the map how far it's moving, and you can really give that value. But the direction really, it shows from the normal mode, and then you do the cross correlation and find the best fit. So that's how they do it in this fitting method. And it was applied in some ribosome structure again. That was a SEC-YEG, a translocon bound ribosome. And there was a long controversy on the orientation of these helices of the SEC-YEG. And so in this normal mode based fitting, they could answer this. I mean, at least they claimed that came out in we were Cell, I guess. So, but after that, whether it was confirmed by any crystal structure or not, that I really don't know. I mean, I don't remember. So, but there they predicted a crisscross kind of helical orientation by the normal mode approach. So this is another one, and then there are some freely available, these all are actually freely available. The race map also you can download, and there are two. This is the Thomas group, they made it, and this is another one I found. These are all normal mode based flexible fitting approach. So then another one is the molecular dynamics based fitting. So this is the one actually which we use, and tomorrow I'll show you in the tutorial how it is used actually. So there this it's a normal MD simulation. How we do this, the trajectory it gives with conformational change as a function of time, and that is the normal MD. But for fitting, what they do, you have to add another potential here, where the EM map is actually the Coulomb potential, and that is somewhere proportional to the atomic number of that atoms present at that region, and that it's somewhere proportional, very crudely if we say, it's proportional to the mass density of that position. That is, if the RNA is there, it's a higher potential is considered, and then the if protein is there, so that is lower, and this potential actually, it's kind of adding pseudo atoms. You can just make it as a potential, and it's a grid steered fitting molecular dynamics. You can say that this term, this will force the structure to go into the highest density region. So that is actually, it's trying to feed the structure. It's targeted. It's targeting the structure to the highest density, and along with that, there is another term is used which keeps the secondary structure. It's a harmonic restraint. It's kept, so it keeps the secondary structure intact. As you already heard, all the mathematical equations actually. I thank Professor Garib, he already explained in the morning. So here also it's just the secondary structures and like cis bonds, these dihedral, and also there are other structures also, like in the all the dihedral of the RNA bases or DNA, and then all the protein structures, they are all restrained. So during the dynamic simulation, that's to take care of the overfitting. It shouldn't break this structure, because anyway we don't, at this resolution we cannot even understand what's the, even if there is a bend in the helix at 10 angstrom, you cannot even, you shouldn't go for predicting that. So all these things you keep you have no, then you cannot, because you have to add hydrogen, everything. After that you put this constraint. So you put hydrogen also, you have to assign the potential, because you have this potential function first, where you put all the atoms potential you have to put. So then you can do, but then you have to really restrain that region also. Like one stretch of amino acids are missing, so you have to really fix these two regions so that they shouldn't move apart. So this you have to really take care. And so the thing is, now say for ribosome fitting. So the RNA regions are actually more dense. So if you start doing the whole protein, RNA, all the whole atomic structure and try to fit it, it will definitely, everything will try to go inside the core RNA structure. So what they suggest that you just do it step by step. Okay, you first do the RNA, fitting of the RNA, keeping all the protein either fixed or remove all the proteins, and then you go for the protein fitting of this. Where is it? Why it has gone? No, it's no. It's. I just want to show this movie because it's a very clear way to see how they do it. I don't know why it's moving away. Anyway. I don't know why it's not showing here. But here they showed it clearly. This movie is available in their website. That you first do all the fitting of the RNA, core RNA structure, and the tRNAs also you can do afterwards, because the occupancy of the tRNAs are actually less most of the time. So the tRNA may not have the same density values, voxel values like the RNA. So first you do all the RNA, then fix the RNA structure, and then the rest of the structure you fit step by step with proteins like there is a protein L9 which is very flexible, and you really get a very little density for this. So after feeding all the proteins, then they fitted the L9 protein at the end. And you have to use a threshold value to remove this threshold, the water, values for the water or the background noise, and you start the values from the RNA and protein. So this is how you do generally. You first feed it. For any this kind of feeding, you have to align the rigid body feeding in the map, and both the coordinate of the atomic structure and the map should be roughly same. If you take a atomic structure and then a map, it never can really, none of this method works. So you have to do a rigid body, or manually in Chimera, PyMol, anywhere you can just put one onto another, and then you can start the feeding, and each of the protein and RNA you can step by step you can feed, and then the quality of the fitting is assessed by the cross correlation, and the best cross correlation is the similar way for most of these methods. Like in race map, they do cross correlation plus R factor. So I mean, it's some kind of adjusting both. It's not that going with only one. So this one was actually applied. One example I can show, because now this method is really used for many proteins, ribosome projects, at least I know. One structure we got, it was like the EFTU-bound tRNA interacts with the ribosome. First, when it comes and delivers the tRNA. And it was about 15 or 16 angstrom map, and we really couldn't make out, couldn't model or fit this tRNA part. It has a kink-like structure. Even in that resolution we could make out, but it was so difficult to really, whether it is some low resolution, some density we are getting or something. But we predicted that that kind of kink is needed because, you know, there is a long-standing question how the tRNA comes in that angle and reads the codon. So it needs to be bent to read the codon, the anticodon to reach the codon. So we predicted that that's the case probably. That's why we are seeing that kind of bend. And then another structure came out which was around 9 angstrom resolution. There also we found that, and there it was modeled this way, and it could fit exactly. I don't know why these movies are not running here. So it was after the anticodon region, when it was fitted, clear kink was seen. So then it was confirmed one way from the cryo-EM. That was in 2003. But then the crystal structure of the same complex came out from Venki's group, which was around 2009 or 11, I don't remember. There they showed that this kink is actually happening when the tRNA reads. So tRNA is really very flexible molecule, and when it reads the codon, it actually bends its anticodon arm. So yes, in this structure you could really see how each of this base and their modifications, everything, how they are placed and how they are interacting. But with this fitting, at least it could be explained that a major change in the conformation that occurs. So there is limitation in the cryo-EM structure, but with this combination of these fitting methods, you really can predict. Of course, that has some limitation also, but still you can predict beyond what we can see in the map. So that if you get a lower resolution map, you can try these methods, flexible fitting. And as I told, there are methods, nicer methods, almost like crystallography refinement, which we saw in the morning. You have done the tutorial on that. So these are the major methods. There are other also different labs developed different methods, but more or less these are the methods used these days. So yeah, thanks. You people are so tired, and yeah.
Thanks, Jyoti, for a nice talk. Questions, any?
Thank you, ma'am, for the nice talk. I just have one question. Is cross-correlation the only way to test the fitness of the fitting, or are there are some other ways to validate?
See, all these softwares, they do it in these different ways. This is the way they do, but you can try. This is the easiest way actually to compare. Like in any other software, you can check the same cross correlation whether the software is giving whether it's correct or not. We generally do because Spider gives this cross correlation. There are commands you can calculate. So we generally recheck this. And another thing I forgot to mention that after you get the model, it should be checked also. There are many validation methods to validate, like how many amino acids are in proper in Ramachandran plot, their right position or not. So all this, there are many softwares now. So it should be checked also. So, but all this is the easiest way, and people, I mean, at least all this method, they standardized it this way, that to estimate.
Very good.
Fading.
Garib, do you want to answer that question? Add on to it? We have an expert who has been working on methodologies for many years.
A little bit pushing too far. On? Okay. Expert is a little bit pushing too far. But obviously it depends what you calculate. Yes, cross correlation in real space has a good side that you can do it locally, and the equivalent of that is in reciprocal space are exactly the same. Potential correlation is exactly same. It has a good side that you can have a look that at which frequency you have signal. Yes, and in principle, probably it would be better to have something that is local in real and local in reciprocal space. And that would be two-dimensional curve. People wouldn't like that. Yes? You like one number. Yes? And two-dimensional. Probably we could do something average cross correlation calculated in reciprocal space. That might be better, because one worry would be that how long could I talk? I can't talk until morning. Okay, probably I should stop at this point.
As long as. I just wanted to maybe there are other factors like goodness of fit in crystallography. How do they differ from cross correlation? Is it very close to each other, or
goodness of fit it depends on how you define it. Yes,
okay.
Classic way of goodness of fit is that a difference divided by variance. Yes, that is a kind of chi-squared. And you could calculate that also, but for example, you could calculate a density minus density divided by variance, but you don't know variance. Yes? And you could calculate in reciprocal space or Fourier space, yes, structure factors minus structure factors squared, the sum over certain numbers, yes, and divided by variance. Again, you don't know much about the variance. Yes. At the end, all these criteria, they are related. There's not, all of them are related. Some of them are more intuitive than others. Yes? But all of them are related because all of them describe that how well your model and observation agree. You could use correlation, you could use R factors, you could use goodness of fit. If somebody says that one of them is better than other, I would not trust that person.
Yes. Very good.
Could you please
Map?
comment? Could you please comment on flexible fitting too? So negative strain EM maps, which is really low resolution.
As I told that what you want to see. I mean, it depends on the resolution. You can feed, but whether you can really get something, it will be like overfitting kind of. If that feature is not there in your map, then what you will explain to that? I never did all the negative strain map, but I don't think that will be very useful anyway. Maybe you want to say anything on that?
Question was that would you use it against negative strain? First answer would be why not. Second answer was that why do you need a negative strain?
Yeah, maybe I'm sorry. Maybe I got another question here, and I don't know if it's proper. I'm really new, so a question is that in all this refinement, do we only consider geometrical optimization, or we also consider energy? Do we consider energy for?
It depends. The real space one, I don't know. Maybe again he can explain. But but there they do geometrical. It has a geometry in the TNT. It has a geometry module, but it doesn't really fix it very nicely. We found that it's in that because it's everything is on one bond. You are just breaking one bond and then fitting others rigidly, and you are trying to fix that one bond. So that is not really very good in real space. But anyway, you only want to see how the helix is moving.
Can I add?
But additional, yeah.
What do you mean by energy?
Sorry?
What is energy?
Energy, we have different energy model, and for example, universal or different energy model. Sometimes we can.
No, you are just saying a few words, and I want to know that how do you calculate? And energy is nothing more than a logarithm of probability, and probability is how well one thing describes another. And if you use a restraint, if you use a fit into the map, yes, all of them are just give exactly same things. You could use a goodness of fit, that is energy. If your energy is a Gaussian distribution.
Actually, my question was trying to say, if we have any restriction at default at the energy, so for bond length or bond angle,
We use bond.
or geometry, but we
Yeah.
have any restriction on the energy.
Okay. Okay. We can talk about that a lot, and we need a few points of PF to discuss that more in detail. Yes. In short, yes. We calculate bond lengths, angles, and torsion angles, and so on. They contribute to energy. Yes. And what is missing is Coulomb interaction. And Coulomb interaction, in principle, is a long-range interaction. Yes? And in principle, they depend on the position of atoms very strongly. Yes? And probably they should not be used when you are fitting a model into the map to describe the experimental data. If you want to describe experimental data, you say that I do not have enough information to derive my atomic model. Yes? And the atomic model should describe the data. If you would use whole energies, then you would have few minimum, and then you don't need experimental data. And you always, people, I think it is all these things, the terminologies, energies, and probabilities, and Bayesian, and all of them are just misleading. And misleading in a sense that you never calculate accurately any of them. Okay? To calculate accurate energy, you need molecular dynamics with quantum chemistry, and then you are in trouble. You don't have that amount of computing power yet. Not only you, whole universe.
Yeah, just to mention that it is actually trying to calculate the molecular dynamics one is trying to calculate the energy, but it's a Newtonian law you are applying. So it's not accurate, but it's giving you some way to keep the stereochemistry and all those things. Ultimately, you are keeping the geometry fixed, but the way you are doing is the MD simulation, which actually trying to see the energy, which is not the correct energy though, as we said. You have to do quantum chemical approach.
Excellent.
Discuss with him.
So excellent. After that energetic discussion, let's
They
go
are so
for dinner.
tired and still they are really so.
Yes, that's good. That's why I'm saying energetic discussion.